Afternoon, everyone. Welcome to the CERIAS security seminar here at Purdue University. So for those of you who are here, thank you for showing up on time in this weather. It's my great pleasure to introduce today's speaker, Ashish Kundu. So Ashish joined the graduate program at Purdue University in 2005, and he's ready to defend his dissertation this semester. And his research advisor is Professor Elisa Bertino. He has done research in several areas in data security and privacy and has won several awards for his research. And today he'll talk about data in the cloud. This is a very topical area. As Randy mentioned earlier, we see there's a cloud out there and it's apparently leaking. But seriously, this is a very active research area. Many companies in the industry and people in research community care about security in cloud computing. And so without further ado, here's Ashish.
Sure. Thank you so much. We're here to present for the CERIAS seminar. And so today's topic would be data in the cloud, how to authenticate such data without leaking. If we primarily look at data, as we there are different kinds of data. One is XML type of data, graph structured data, and also data that are like tabular data. Today the topic will be primarily on XML or graph structured data. So this talk I'll be focusing on the relationship between privacy and leakage of structural information. Okay, and after that will present two schemes for authentication of data without leaking. Okay, so let's see the relationship between privacy and leakage of structural information. In the meantime, I'll request excuse me sometimes because I have allergy and sometimes my eyes are watering, so I might do this in between, so sorry for that. Okay, so if over the last decade or so there has been a lot of work and lot of interest on third-party data distribution, and over the last few years it has picked up with the buzzword cloud computing. What happens is that with third-party data distribution or cloud computing, economies of scale are achieved by the different enterprises, businesses, and by the government, while managing the increasing amount of data due to data explosion, and also they are able to focus on their core competencies. Okay, now while such data explosion has continued to happen, what is being required is that can we have services that can manage such data, that can analyze such data and also archive them, okay, which lead us to the cloud-based services. Okay, there are several companies in the forefront of cloud computing like IBM, Amazon Web Services, Google, Microsoft. And so therefore, if we look at the requirements of services delivery on cloud computing, as that on-demand and seamless requirement is a major requirement. The services should be scalable, dependable, as well as secure. And today's talk is focused on security primarily. Okay, some of the important areas or verticals on which these services are being offered are healthcare, genomics, content management, and business analytics. And today's motivating example would be on healthcare services. Okay, we'll start off with showing that how data leakage is important in healthcare services and how we can address it. Okay, one of the important aspect of healthcare services is that they manage and share electronic medical records. Okay, and in fact, the High-Tech Act of United States recently is actually providing incentives to organizations to manage and share electronic medical records. Okay, so let's look at a common scenario in healthcare services. A common scenario is a doctor's system generates or updates an electronic medical record, and that medical record is uploaded to a cloud-based healthcare service. Okay, and what happens is that the nurse's device makes certain queries, or maybe it has subscribed to the cloud-based healthcare service for event notification or notification of the data. So it receives the part or the complete EMR. Okay. However, the other than the requirements of scalability, dependability, as we talked, security and privacy are very important, and they are required by HIPAA and EU directives. Okay. So what security threat that we are going to address in today's talk? There are two types of threats. The first threat is that the electronic medical records or the data associated with these records can be tampered. Okay, they can be tampered through man-in-the-middle attack while they are on transit from doctor's system to the healthcare services, or healthcare services to nurse's device. Okay, the third-party service provider may be semi-trusted or vulnerable. Okay, and therefore data integrity may be a concern at the service provider itself. Okay. And the question is whether the EMR from the authorized source, means the nurse should receive the corresponding EMR from the specific doctor. It should not receive it from some other doctor. Okay, that will be a big problem. So authenticity is a big requirement. Okay, the second threat is of privacy, that the nurse's device must receive only that amount of data that it is supposed to receive. Okay, it should not receive more than that. Okay, so let's look at let's look at a concrete example and see what do we mean by this. Okay, a simple EMR in XML is given in this example because XML is becoming the standard specification language for EMRs. Okay, in this example, there are the patient has suffered from 3 diseases: cancer, kidney stone, and heart attack. And the order between these nodes are important: G3, G4, and G5. That is, let's say the kidney stone occurred after cancer and heart attack occurred after kidney stone. So there is a temporal order among the siblings. Okay. Now, the first security requirement of authenticity or integrity translates to that the nurse's device should be able to verify the authenticity of the received EMR. Okay. And what do we mean by authenticity? When we say authenticity of an XML document such as the EMR, we mean the authenticity of the contents of each node, the parent-child relationship between the nodes, and the sibling ordering between the nodes, left-right ordering. Okay, and the fact that the EMR is genuine and is from the authorized source or from the specific doctor. It's not from somewhere else. Okay, so the second threat, or leads us to the second security requirement, is that the privacy protection must be enforced. Okay, so the nurse's device should only receive parts of the EMR that it is supposed to receive. The other parts are hidden. Okay, so in this case, if the nurse is allowed to carry out, a nurse is allowed to carry out a treatment of cancer, okay, then it should only receive the highlighted subtree G1, G2, G3, G6, and G7. It should not receive G4 and G5. Okay. Now, so there are two requirements, right? The first requirement is authenticity. The second requirement is privacy preservation. Okay. The question is, how do we verify authenticity of XML documents then? Okay. There is a foundational technique which has been since '78 from Stanford, is Merkle hash technique, and it has been widely used. It has been applied to healthcare solutions also. For example, Devanbu's paper on Journal of Computer Security and Thompson's work in PETS 2009. For example. However, the markerless technique leaks information, therefore it violates privacy. Okay, so let's see how it violates, how it leaks information. The markerless technique works as follows: that we create the Merkle hash of the root of the tree. Okay, the tree is bottom up. Okay, for example, there is a root. We create the Merkle hash of the root and sign that Merkle hash, and the signature of that Merkle hash of the root is the signature of the tree. Okay. Now, that is, we create the Merkle hash bottom up, left to right. Now, let's look at our example. The example here is the EMR tree we have. Let's look at G2. The Merkle hash of G2 is computed by taking the Merkle hash of G3, Merkle hash of G4, Merkle hash of G5, concatenated together and prepended with the content of G2. Okay, and then it is hashed again. The hash is a collision resistant hash function here. Okay, and by collision resistant it means that it is one-way hash function. Okay, so the signature of the EMR tree is essentially the signature of the Merkle hash of G1. Okay, now what happens is that the doctor system computes the Merkle hash of the EMR tree, signs it, and uploads the EMR as well as the signature of the EMR to the cloud-based healthcare service. Okay, so excuse me. Now let's look at the interaction. Now the nurse's device is going to receive the highlighted subtree, that is T delta G1, G2, G3, G6 and G7. So what happens is that for the nurse's device to verify the authenticity of the received subtree using Merkle hash technique, it has to receive the following information. It receives obviously the signature of the EMR tree, right? It has to receive that. It receives the EMR subtree, of course. Okay, it receives other information. Those informations are essentially necessary to compute the Merkle hash of G2. Okay, they are the Merkle hashes of G4 and G5, because those nodes are not allowed. The nurse should not receive, nurse's device should not receive those nodes. So it receives the Merkle hash of G4 and G5. It receives the fact that G2 is the parent of G4 and G5, and the ordering between G3 and G4 and G4 and G5. These are the information, and they seem to be basically harmless to us at this time. Okay. Okay. However, the problem is here that it receives more information or auxiliary information, and using this auxiliary information, nurse's device can infer private information. How? Let's see. Okay, these are the leakages. That the fact that again the leakages are the fact that Merkle hash of G4, Merkle hash of G5, the parent-child relationship, and the sibling ordering. Okay, what the nurse's device can infer? The nurse's device can infer by knowing that G2, G4 is a child of G2 and G5 is a child of G2. Okay, and G3 is left of G4 and G4 is left of G5. It can infer that the patient has suffered from another two other two critical diseases. Okay, this is a very strong inference. Okay, and it also tells the temporal order between them, because that the disease with respect to G4 was suffered by the patient after cancer, and the disease with respect to G5 was suffered by the patient after the G4. Okay. Another inference is that since G6 has only one child, that the patient has gone through only one chemotherapy instance. That is another strong inference, right? Moreover, if the Merkle hashes have not been computed appropriately, or the hashing system has not been implemented appropriately, dictionary attacks can be carried out. Okay. So, In fact, even by using existing Merkle hashes, what they do is that they leak length of the strings and they leak certain information. They are not fully confidentiality preserving. Okay. So therefore, we have seen that the Merkle hash technique leaks information. The second security requirement therefore of privacy is therefore is not protected or supported, and therefore any system that uses Merkle hash technique for supporting cloud-based healthcare solutions is not HIPAA compliant, even though they are claiming to be HIPAA compliant. Okay. Okay. One thing is, please feel free to ask me questions, interrupt me. Okay. Let's make it interactive if there is any question. Okay. So the summary is that Merkle hash technique leaks, and ours is probably the first such work to connect. To bring in the connection between privacy and leakage of structural information and its solutions. Okay, so going back to the EMR subtree or EMR tree, that a given healthcare record, so the left side is not a valid subtree that a nurse's device should receive. Okay, it should receive only the right hand side, because there should not be any auxiliary information about the subtree that should be given to the nurse's device. Okay. Now the question is, how do we do that? Okay. The question is that how to authenticate a subtree without leaking. More precisely, how do we authenticate a subtree T delta without leaking T minus T delta? By T minus T delta means the set of nodes and the set of edges that are in T but not in T delta. Those information should not be leaked. Okay. Our schemes, we have solutions for trees and order trees and order graphs and forests, and is efficient. Okay. Our overall approach is different from Merkle hash technique. In Merkle hash technique, when we compute the hash, we essentially encode the ordering or structural relationships between the trees, between the nodes in the tree, in the computation of the hash. Okay, we do not want to do that. What we want to do, that we want to encode the structural information in the nodes and then create the hashes and sign them. Okay. So the first solution will try to solve the problem for a single subtree, and later on we will go into a solution that leads to a multiple subtrees. Okay, we call this solution as structural signatures for trees, which has actually have been extended by other researchers in cryptography area, and have been formally defined, but it is in SENS 2010 paper there, and but their formal definition is actually not correct. Okay, our next paper will complete their formal definition and give a better solution. Okay, so the central observation of this solution is based in graph theory, is that when you take a tree, okay, when you assign the pre-order and post-order number to those nodes, okay, by pre-order post-order numbers mean that a depth first numbering of the nodes in the tree. Okay, pre-order means anytime you visit a node you number it, and post-order means anytime you visit a you give a number to the node means you have already given such numbering to all its children. Okay, that's the pre-order and post-order numbering. Anytime you give a post-order number and a pre-order number together to each node in the tree, such sequences of the numbers can be used to easily reconstruct the structure of the tree. Okay, let me repeat that again, that by using the sequence of pre-order and post-order number of the sequence of vertices, one can easily reconstruct the structure of the tree. Okay, what it means is that the pre-order and post-order numbers have inherently represent the signature of the structure of the tree. Okay, we are going to use that property. So in this case, for example, the first part, the number 7 is the post order number of G1 and number 1 is the pre order number of G1. So the pair means post order number and pre-order number. That's the convention we have been using. So anyway, okay. So what we do is that we encode each node with post order and pre-order numbers. Okay, that requires only one depth first traversal. However, the relationship between post order and pre-order number is that the parent of the parent node always has the larger post order number than all its child node. Okay, and reverse for the pre-order numbers. That is, the pre-order of a parent node is always less than the pre-order number of the child nodes. Okay, sibling order for is that the pre-order number of a left sibling is always less than the pre-order number of the right sibling, and similarly for post-order number of the left sibling is less than the post-order number of the right sibling. And when we are going to verify the authenticity of the of a subtree, we are going to use these properties. However, the vanilla or the standard form of post-order and pre-order number leak information, because if I give you that G7 has the post-order number 1, means it's the left node in this tree, in the original tree, right? It leaks a lot of information. So, and there are more information that can be leaked by the number 7, because it says that there are the number of nodes preceding this in the pre-order traversal. The such number is 6. Okay. Therefore, in order to prevent these leakages, we define a notion of randomized traversal numbers. Okay, we call them as randomized post-order numbers, RPONS, and randomized pre-order numbers, RRONS. Here we are talking only about non-binary trees. Okay, when we come to binary trees, we have to represent them either with a notion of randomized in-order numbers. Okay, and either of randomized post-order numbers or randomized pre-order numbers. Okay, now each of these randomized traversal numbers are of have a large bit length, that is either 256 bit, for example. Okay, how do we compute such randomized traversal numbers? Is what we do. The easiest solution is that you generate n number of random numbers. N is the number of nodes in the tree. Okay, generate them and sort them. Right. So that way, and then that sorted number essentially represents the sorted the post order numbers in that order. Similarly, do this for pre-order numbers. Okay, does it work? It should work, because if we suppose a tree has a million nodes. Okay, you generate million number of random numbers, sort them. Now, if from the sorted numbers we can sorted random numbers, we can know what is the next random number that would be generated. Okay, then we have broken the random number generator. Okay, so okay, we can talk about that later. There is a very low probability that the distance between these random numbers might be uniform, but that is very, very low. Okay, so therefore our scheme is practical. Someone can argue that this is weaker security, but it is practically secure. Okay, I will come to a probable security solution in the latter part of the talk. Okay, so what we do then is that we replace these post-order numbers and pre-order numbers by randomized post-order numbers and randomized pre-order numbers. Okay, so here in G1 we had 7 and 1 here. We replace that by 538 and 143. Okay, that pair we call that structural position. Now we will create the hash of the nodes. Okay, we will take the randomized post-order number and randomized pre-order number, or 538 to 143, and the node contents. Okay, concatenate them together and give it to the hash function. Okay, and that output, the output of the hash function then is called the integrity verifier of that node. Now the question is, how do we sign? Right? In Merkle's technique, we used to sign the root of the Merkle hash of the root of the tree. Okay. In this case, we are going to sign the integrity verifier of each node. Okay. In fact, we have a solution in which you do not have to sign each node integrity verifier. Okay, we need to compute only one signature for every tree. Okay, that is yet not published, and so I cannot talk about that today. I'll talk about what is published today. Okay, so we'll talk. The solution that I'll discuss today is based on condensed RSA. Okay, it's not. We have solutions with aggregate signatures using bilinear maps by Bonnet. Okay. How do we sign using RSA? That we take the integrity verifier for every node. Okay, and we sign it using RSA. How do we sign it? By raising it to the power of the private exponent of RSA and mod of n. N is the public modulus of RSA, or RSA modulus, I should say. Okay. Now the signature of the tree is the we generate a salt for the tree. Okay, the salt is necessary to for a nurse's device or for a user to not to be able to tell whether the received subtree is actually identical to the original tree or not. The salt prevents that. Okay. Now, we condensed RSA means we condense all the signatures of the nodes by multiplying them together through modular multiplication. Okay, with the RSA modulus. So that's the signature of the tree. Now going back to our example, the doctor system computes such signature of the EMR tree. Okay, and uploads the signature of each node and the structural position of each node along with the EMR tree. Okay, so if we look at now, let the user be insurance provider B. Okay, the insurance provider is going to say that, okay, select all the digits or all the critical digits where the insurance provider name equals to B. Okay, and suppose the insurance provider covers only cancer and heart attack. Okay, so therefore the subtree that will be received by the client or the receiver is this one: G2, G3, G6, G7, and G2, G5. Okay. The healthcare service, before it sends the subtree to the receiver, it computes the signature of the subtree by condensing the signatures of all the nodes. That means every node has a signature, right? It multiplies them together with modulo n. Okay, and it sends that signature, the signature of the subtree. It also sends the structural position of each node, because that is a critical component in our system. Okay, so now when the receiver receives the subtree, what it does is that it computes the integrity verifier of each node by taking the structural position of the node. Let's say G3 has a structural position 48,521, and the content of G3, whatever is received, okay, pass it through hash function. It becomes, that hash value becomes the integrity verifier of G3. Okay, so once the hash function results in the integrity verifier, what it does is that the receiver then takes the condensed signature of the subtree, okay, raises it to the power of the public exponent. It basically does a RSA verification. Okay, and whether that value, okay, is same as the product of integrity verifier of all the nodes, modulo n, of course. Now if it is same, then the contents of the nodes are verified. Okay, however, we have not yet verified the structural integrity, because structural integrity is important in terms of parent-child relationship and sibling order, right? So that can be carried out by the properties of post-order numbers, randomized post-order number or randomized pre-order numbers, right? Remember that we talked about that the parent-child relationship has this property, that parent always has the larger post-order number than the children, and pre-order number of the parent is always less than the pre-order number of the children. Okay, so such a test is applied, and the sibling order test is that the left sibling always has the less pre-order number and post-order number than the right sibling, than that of the right sibling. Okay. Okay. So authentication is finished. Now let us see how our system leaks information. No, because if we look at to the client, we have not given any information about G1 and G4. It only received. Okay. It only received this subtree, right? It did not receive any other information. Okay. And can the receiver infer that there is a node G4 in between G3 and G5? No. Yeah.
But here the receiver gets information that G5 occurs after G3.
Okay.
But that information the receiver doesn't ask.
No, that information is necessary here.
He asks only for G3 and G3. He just asks for the diseases which the person got. But here he gets the ordering of the disease also.
Okay, so that's the query model. The query model, when you query for diseases, it will not just give you the node containing the disease names. It will give you what medication that the person has gone through, because those medication charges will be actually be borne by the insurance provider, for example, okay, or which doctors have carried out the treatment, right? So therefore, it needs to have parts of the subtrees, okay, based on the access control model. Okay, here we have not talked about access control model or the query model. Okay, so we assume that the receiver or the insurance provider will receive this subtree due to that query. Did I answer your question? Okay. Okay. So, in another interesting property of this technique is that we can easily reconstruct the structure of the tree, as we said earlier. So therefore, the cloud service does not have to provide the structural information to the receivers. It does not have to tell that, okay, these are the parent-child relationships or the edges, and these are the sibling-sibling ordering. Okay, it just have to provide a bag of nodes to the user. Okay, and the user can easily reconstruct the structure of the subtree. Okay, and that is quite efficient in n log n time, and because of sorting. Okay, so okay, now let's go to the next point of many subtrees. Can this solution share many subtrees of a given tree without leaking information? Okay, let's say query 1 results in some arbitrary query, okay, G6, G7. Query 2 results in G1 and G2. When the receiver has both G1, G2 and G6, G7, it actually learns about the path between G2 and G6. Okay, so it is not completely non-leaking for many subtrees. Okay, the user essentially learns an induced subtree that covers all the subtrees that it has received. Okay, so it has applications in privacy preserving data mining to a certain extent. Okay, but for our requirement, it is not what we require. Okay, so the summary for this technique is that it authenticates subtrees, and it is leakage free for one subtree and induced subtrees. Okay, it is efficient because we'll see the performance costs. Then the transmission cost is number of nodes. Okay, it doesn't send any auxiliary information. In Merkle's technique, you have to send about 2 log n of information. That is minimum because of the auxiliary information that you have to send. Okay, and it is simple to implement, very simple. Okay, now the problem of many subtrees. In this requirement, the consumer should only learn the individual subtrees. It should not learn any relationship, any parent-child relationship or path relationship between the nodes. Okay, so the problem is, how do we authenticate such many subtrees? The idea is that we assign, instead of assigning the post-order and pre-order numbers to the nodes, we assign something called a secure name to each node. Okay, and this secure name is used to verify the sibling ordering or the ordering between the nodes. Now, such secure names can be used to protect or reason about sibling ordering, and can be used to verify the parent-child relationships also. Okay. So, and are probably leakage free. Okay. Let us look at what do we mean by a secure name. Excuse me. Okay. The secure name has two parts. The secure name has n bits. N is large. For example, 256 bits, or even larger than that, 512 bits. Okay. There are two parts, left part and right part. Left part has L bits, right part has R bits. Okay. Initially, the left part bits are unused, all of them. Okay. Now, the security parameters, of course, are L, R, and in fact, if the tree has k branching factor, means every node will have at most k number of child. Okay. Then the L minus 2k is a security parameter. Okay. I will not go details of why it is so. We can discuss that later. Now let us look at this simple tree where U is the left sibling of X. Okay. So how secure names would help is through the notion of sibling order test. Okay. In this test, what we do is that we find a jth position in the secure name of U and X, and j prime position in the secure name of U and X. Okay. The sibling order test says that if you take the XOR of the jth bits in both of the secure names, and if you take XOR of the j prime bits, okay, the XOR value of the jth bit should be less than the XOR value of the j prime bits. Okay. What that means that the jth bit, their XOR should result in 0, and XOR of the j prime bit should result in 1. What is the probability of happening that the jth bit is 0? It's half actually. Because if we look at the all possible bit assignments for the 4 bits, it is 0 0 1 0 0 1 1 1, right? Only 2 of them satisfy that jth bit would be 0 and j prime bit would be 1. So therefore the probability remains half, which is a requirement for security here, right? Because with almost negligible probability, an adversary should be able to come up with a new secure name, or should be able to say that okay, the j prime bit should be 1 here for an unknown sibling. Okay, so how do we compute these bit positions? Okay, the bit positions are computed as, first we assign a random to the right part of U. Okay, and then we assign a random to the right part of X, Rx. Okay, and the jth bit position of the left part of both U and X secure names are like this, that we take, since the ordering is U is left of X, therefore we take right part of U and right part of X, concatenate them together in that order. Okay, then take mod of L. L is the number of bits in the secure name. Okay, so therefore what is happening, what we are getting is a position on the left part from 0 to L minus 1. That becomes the jth position. Okay, for j prime position, okay, what we do is that we reverse the ordering between RU and RX, okay, and concatenate them and then take a hash and mod of L. That becomes the j prime position. Okay, and if either of them have been used, we repeat the procedure by taking new RU or new RX, or both of them. Okay, now we assign the values to each of the bit positions such that the sibling order test is valid. Okay, now okay, I had to run faster on that actually. If you have questions, please feel free to meet me after the talk or interrupt me here. So the secure names are actually probably leakage free, okay, and they do not leak anything about G4. For example, if a user is given G3 and G5, the user cannot learn anything about G4 from the secure names. That is a major requirement. But the user can verify the order between G3 and G5 using the sibling order test. Okay. Computing the secure names are very efficient. Okay. The number of restarts required for a 25 array tree, okay, is about 11, okay, which our performance evaluation says that is almost nothing. Okay. Similarly, and as before in the structural signatures, we compute the integrity verifier of the nodes, and for the parent-child relationships we have two options. Either we assign a different secure name for the parent-child relationships, or we take a hash of the edge. Okay. So signing is carried out using condensed RSA or aggregate signatures. Now what happens is that the service then computes the redacted or the signature of the subtree, okay, and it sends the signature of the subtree and secure names for the nodes, and it sends to the insurance provider. Authenticity verification is carried out as earlier. Okay, the difference here is the structural integrity. In order to verify the parent-child relationship, if we have used an edge verifier, means we have hashed the edges, therefore then it has already been verified through content authentication. Otherwise, we can use the sibling order test again for carrying out parent-child relationship, also sibling ordering. So we apply the sibling order test between the secure names by computing the J and J prime that bit positions again, and then checking whether the XOR of the Jth bits in the two secure names is less than the XOR of the J prime bits. Okay. The security of the scheme is depends on authenticity and leakage free. Our leakage free, our secure names are actually indistinguishable against adaptive chosen ciphertext attacks, and the authenticity is also secure against existential forgery. Okay, now let's go into graphs. How do we solve for graphs? In fact, we have solved the solution, the problem for graphs, because in our scheme we only consider the ordering between the nodes and the ordering between the parent child. Okay, therefore we are not concerned about whether an edge is a back edge or whether an edge is a cross edge or not. Okay, if we extend this the second solution, it can be directly applied to graphs. For example, directed acyclic graphs. For cyclic graphs, they are ordered in the following sense. Of course, cyclic graphs in general cannot be topologically ordered, therefore saying that ordered cyclic graphs doesn't make any sense. But if we look at XML data, there are a notion of IDREF, the references, and those different types of edges that result from these IDREF attributes can result in some form of cyclic graphs. Okay, so therefore our general scheme, or that the second scheme can handle that. We have extended our first scheme, structural signatures for trees, to directed acyclic graphs and graphs with cycles. That is a little bit complicated, and which is why I didn't talk about that here. That has appeared in EDBT 2010. Okay. So, okay, how about forests? Forest means there are disconnected components. Okay. What we do is that we connect them. We take these kind of disconnected components and connect them by adding intermediate vertices and another vertex. Okay, if there are k of them, we do the same. We take the same approach. Okay, and then sign them. Why does it work? Because at any point of time, the receiver or any legitimate user will not have access to these dummy nodes that we have added or edges. And since our scheme does not leak any information about nodes and edges that the user doesn't have access to, therefore it doesn't tell the user whether there are these dummy nodes or not. So therefore the user cannot even know whether it is a forest or it's a graph or it's a tree. So the advantage here is that the user cannot even know whether it is a tree or a graph. That is important, because if the user knows that it is a graph and not a tree, means there are extra nodes, it might leak information. Okay.
Excuse me.
Yep.
Why can't we just add G12? Why are we adding 3 to connect them? 3 nodes.
3 nodes. Okay, that's a very good point. The point here is that in order to verify the integrity of G10 and the ordering between F1 and G1, okay, we need to provide the secure names for G10 and G11. So it's not clear now. If we go back to our second scheme, it will become clear. Otherwise, there will be a leakage of that. That there is a common node. If we remove these 2 nodes, the user might infer that okay, F1 has G12 as the parent, G1 has G12 as the parent, and therefore it will say okay, there is a common node, common ancestor node. Okay. So the performance of the leakage-free scheme is that we used a ThinkFed to see how bad or good our performance is, and the computation of secure names is very fast, right? If we take a 300 array tree, which means a node has 300 children. In fact, that will result in a huge tree, about 27 million nodes at the height of 3. Okay, so 300 is a very, very large arity of a tree. Now, what it shows is that the rank of a node, like if we take 300 nodes, the rank is I, the ith sibling there is the I is the rank of the node. Okay, so the rank of the node versus the time it takes in millisecond to compute the secure name. Okay, for the 300th node, it takes about 3.5 milliseconds. Okay, that means that the secure names for 299 other siblings have already been computed. Okay, so this is because it has to actually retry and figure out which bit positions J and J prime would work for it. Okay, and signing it because of RSA is expensive. Okay, because of its modular exponentiation, it takes about, for a million node tree, it takes about 16,000 seconds, which is large. But if we can parallelize it, remember that it was carried out on a ThinkPad, okay, of limited capacity. If we are doing this on a larger system and we can parallelize it into multiple cores, it will become it will reduce the performance will improve drastically, or will improve greatly. Okay, so verification, or the red one is our scheme, the blue one, dotted one is the Merkle's technique. Our verification scheme does better than the Merkle's technique. I didn't mention Merkle's technique in the previous plot because Merkle's technique computes only one signature. Okay, so therefore it's very efficient in terms of signing. Ours, we compute a million number of signatures for million number of nodes. Okay, so in our scheme does better than Merkle's technique primarily because it does not need to receive the auxiliary information. Okay, auxiliary information are the information about the nodes and the relationships or the parental relationships that the user does not have access to, right? And which was originally the sources of privacy violations, right? Okay, there has been a lot of related works, not on this problem, but on periphery of this problem, is that there has been a lot of work on authenticated data structures, okay, but none of them have been designed to be leakage free. Okay, for example, Goodrich and their recent paper in 2009, okay, it talks about graph authentication. It essentially generalizes the Merkle's technique to graphs using a notion called path hash accumulator. Okay, but that leaks. So there have been works on by Papamanthu on authenticated hash table in CCS 2008. Okay, the original work came by Naur and Nissim in 1998. Okay, so the more closer work is by homomorphic signatures. It started off due to a talk by Rai West in 2000 on transitive signatures, but none of them are leakage free. In fact, the work have actually focused on linear structures like chains. Okay, we took a more complex problem by looking at nonlinear data structures like trees and graphs. Okay, and we solved that problem. In fact, since we have a solution for trees and graphs, means we have solutions for paths. Okay, which actually have been an open problem. So our conclusion is that we showed how privacy is related to leakage of structural information. We provided a solution for single subtrees or induced subtrees, which is called structural signatures. We have a general solution for ordered trees, DAGs, and graphs with cycles and forests. That is called the leakage-free authentication scheme. And these schemes are efficient. In fact, there is a scheme that is much more efficient than this, which I didn't talk about today and has not been yet published. So, but future works that we are thinking of pushing this scheme for XML, the standardization of XML signatures. We have a work on authentication of objects. When we take an object, it is an object graph, and it basically leads to in a web services you have to share objects. How do you authenticate objects? And we have an ongoing work for authentication of emails. Okay, so this is it for today. Thank you very much. Please. Sorry, I took